lose some time because our time is quite tight. All right. Okay, so it is okay, so we see the sections here. Yeah, so our helper Harsha has already shared the video. Okay, so let us start our section. All right. Yes, Harsha?
This is just the sponsor slide. Do we want to start?
Yes, I think we should start, right? We are, it is about time for us to start, yes.
Okay, I'll share the first video.
All right.
Want to introduce the paper and the speaker?
Yes, let me introduce first, okay? So hello everyone, my name is Reyno Jiang from the University of Hong Kong, and I'm the section chair for this round number 12. So the first speaker of this talk titled Efficient Approximation Algorithms for Adaptive Target Profit Maximization will be done by Dr. Jing Tang. So Dr. Jing Tang is currently a research assistant professor at National University of Singapore. His research interests include big data management and analytics, online social networks, distributed systems, and network economics. His work has been published in top conferences and journals such as SIGMOD VLDB, ICDE, ICNP, ICDS, and Infocom. And a number of journals, including VLDB journals as well. And he received the Best Paper Award from the ICNP 14 conference. So without further delay, Dr. Jing Tang, okay, can you start your talk?
Okay.
Can you talk a few words about your talk before we broadcast the video?
Okay, that's fine. Okay, today I'm going to present our work on target profit maximization. That is about the viral marketing in social networks. So I'm going to present to discuss how to promote the products and new ideas, opinions through social networks like the advertisements. So let's see what will happen through the video.
Thank you. Yeah, Harsha, please play the video.
My talk. Today, I'm so glad to present our work on adaptive target profit maximization, a joint work with Clique, Xiaokui, Aixing, and Andrew. So first, I'd like to introduce you some basic information about this topic. I believe you guys every day use social networks like Facebook, Twitter, Instagram.
Constant, 1 second, can you pause?
Actually, they are wrong.
The video is not clearly visible. There are some gray boxes around it.
Yeah, maybe you need to refresh it again.
I will try again.
Yes.
Okay, yeah.
More than 1/3 global population. So due to such huge amount of social networks, people are thinking about business. Advertisers choose to promote the products, ideas, or opinions through social media. In fact, this year they spent more than $100 million on social networks. So an actual question is, how can we make success advertisements through social networks? In this talk, I'm going to answer this question. The marketing, or say the viral marketing business in social networks is based on the influence spread, the word of mouth effects. So imagine that what will you do if you say the discussion of COVID-19 on your Facebook, probably influenced by these users on your Facebook. So Then you will post similar status on your Facebook or Twitter or other platforms to influence your friends, your neighbors, so on and so forth. Finally, a lot of users on social networks discussing COVID-19. This is the facts. So in this work, we consider a probabilistic social network to model the influence spread or the information diffusion. We consider each edge is associated with a probability PUV to represent that the probability a user U influence his neighbor V. So due to such kind of randomness, we can observe, we can get different results of influence diffusion. We call it realization. This is a random process. And our target is to maximize the profit by selecting seed users from the social network. Note that the profit metric combines the revenue of influence spread and the cost of seed selection. So I believe the company or the advertisers care more about the profit rather than the revenue, right? Meantime, we observe that some advertisers or the companies normally can access a part of the social networks due to the privacy, due to the competition issues. For example, the shop owners can only provide or invite the users on the subscription list. They cannot access the entire social networks. So in fact, in this work, we look at the target profit maximization problem. Note that this problem is a generalization of profit maximization, because if the target set is the entire set, then target profit maximization is exactly profit maximization. The conventional solutions for viral marketing programs look at the non-adaptive strategy. For example, if we want to select 2 seed nodes, the classical solution then select 2 seed nodes in one batch. Then to observe who will be influenced by the 2 seed nodes. For example, in this case, another 4 users will be influenced by the 2 seed nodes. So a total of 6 nodes are activated. However, we are looking at a more smart way. That is, we look at the adaptive algorithm. We first select 1 seed user. We then observe who will be influenced by this user. In this case, another 5 users are influenced by this user. Based on this feedback or this observation, we select the next seed user. In this case, we select this one and to observe who will be influenced. So by our adaptive algorithm, a total of 8 users are influenced, are activated, much more effective than the non-adaptive algorithm, right? So in this work, we look at the adaptive target profit maximization. That is, we attempt to find an adaptive policy pi to maximize the expected profit over all possible realizations. We note that the profit function is submodular but no longer monotone. The submodular is very important property. Based on this, Beck-Binger proposed double greedy algorithms that can address such kind of problems under the non-adaptive setting with strong theoretical guarantees. Our solutions are also motivated by the double greedy algorithm. So let's see how the double greedy algorithm works. This algorithm works very simple. but very elegant. It just compute the marginal profit of keeping this node or removing this node, and compare it. If keeping this node generates higher profit, then just keep it. Otherwise, remove it. Makes sense, right? So here is our adaptive double greedy algorithm. The key difference is that we also examine that whether this node is activated or not. If yes, we just remove it and continue. Otherwise, we compute the two functions and compare it. If removing generates higher profit, we just remove it. Otherwise, we keep it and add it to a set S. After that, an important procedure is to wait and observe who are influenced by this seed user. In this case, some users are influenced. We then remove these nodes. We examine next seed users. For example, we find that V2 is already activated by V1. Then we simply remove this node and continue. So on and so forth, we finally find a set of users, and this policy is adaptively based on our observation or the feedback. So we prove that our policy can obtain a constant factor of 1/3 approximation ratio compared with the optimal policy. This is very promising, right? However, this result is under the Oracle model. That means we can query the profit function or the inference spread function of any node using big O one time. You may know that the inference spread is difficult to compute, especially for the large-scale social network. So to tackle this issue, we consider to estimate the inference spread by using additive error. So here is our algorithm. We first set an initial error, and then we compute the two functions. Because we have error, so the two functions become two ranges, no longer 2 points. So in this case, they may overlap each other, so we cannot distinguish them. In this case, we just reduce the error, then we re-evaluate or re-estimate the two functions until we find that the two functions can be separated clearly. We choose the larger one, or the error is small enough, we can terminate also. We prove that this algorithm, by taking into consideration of the sampling error, we can provide theoretical guarantees also. However, this method has some problem. For example, imagine that if a node has a large inference spread, then the additive error is relatively small. So we know that if the error is small compared with the expectation, then we need to take a long computational time, which is not good. So to tackle this issue, we propose a new sampling method that is a hybrid error, combining the relative error and the additive error. The rationale behind this is that, imagine that if the inference spread is large, then the relative error will dominate the entire error. Otherwise, if the inference spread is small, then the
additive error will work. So it's a good balance. This is our algorithm. We first again set initial errors, the additive error, the blue part, and the relative error, the green part. So if the two functions overlap, then we reduce the error to further compute the two functions. If they are still overlap, then we further reduce the errors until they can be separated. We choose the larger one, or the error is small enough. Finally, we prove that our algorithms can still obtain theoretical guarantees. More importantly, it can speed up the entire procedure by a factor of epsilon n factor. So to evaluate our proposed solutions, we use several real-world data sets. For example, the live journal data set have millions of nodes. We compare with some baselines, especially some non-adaptive algorithms. This figure shows the results of different algorithms, the profit generated by different algorithms. As can be seen, our algorithms, the blue line with triangle markers, they generate much higher profit than the baselines. This figure shows the running time of different algorithms. Although our algorithms run slower than the non-adaptive algorithms, the running time are quite acceptable. So to summarize, in this work, we study a novel problem of adaptive target profit maximization. To our knowledge, this is the first work to study such a problem under the adaptive setting. We propose several solutions to address this problem under both the Oracle model and the noise model. We prove that our algorithms have strong theoretical guarantees. Moreover, we conduct several experiments to demonstrate that our algorithms outperform the baselines, especially the non-adaptive algorithms, significantly in practice. So that's it. Thank you very much. I'd like to take your questions.
All right, thank you. We only have, we can enter in one question, okay? Any questions from the audience?
This is Lax. Can I have a question?
Yes, please.
Hi, Lax.
Yeah, hi. Thanks for the talk. Very interesting. I have a lot of questions, but I will restrict myself to one and a half questions in the interest of time. So in prior work, so as you know, I have worked on adaptive influence maximization, both in our group and also with Shakwe. So it has been our finding that when it comes to maximizing influence spread, the gain in adaptive approach compared to a non-adaptive approach is not significant. However, when it comes to minimizing the seed, the number of seeds for a given target, so obviously the problem is minimization. There we found that the minimization achieved by adaptive approach is significant compared to the non-adaptive approach. So in your experience with profit maximization, you seem to be finding that there is significant gain even in the case of profit maximization when you use an adaptive approach. Can you shed some light why that is so?
Okay, very wonderful question. In my opinion, I agree that in adaptive influence maximization, the advantage of adaptive algorithm is not significant. That's because due to because the submodule function as you can see, if you the marginal gain of the seed nodes reduces along with the when we select more nodes, right? So even though we apply the adaptive algorithms, we can achieve a slightly higher influence spread compared with the non-adaptive algorithm. However, for adaptive seed minimization, again, due to the submodularity of the influence spread function, if we want to achieve a certain threshold, for the last certain threshold, we need more seed nodes, right? So as a result, we need. It looks like the adaptivity of the adaptive algorithm can have more advantage under the for the adaptive seed minimization problem. So for adaptive profit maximization problem, it depends how we set the cost. So if the cost is a uniform setting, the profit maximization under the adaptive setting is still not significant. But for some other setting of the cost of seeds, maybe the advantage of the adaptive algorithm is more significant. Yeah, that's my opinion, my experience.
Makes sense. Thank you very much.
Thank you. Okay. Let us thank the speaker again for the interesting talk. Okay. Thank you. Okay. All right.
Thank you.
Thank you. So without further delay, let us go to the second talk, which is about the efficient Bitruss decomposition for large-scale bipartite graph. So the speaker today is Kai Wan, who is currently a research associate in the database group at the University of New South Wales. So Mr. Kai Wan, can you say a few words about your talk before we start playing the video?
Okay, so in this paper, we will talk about the Bitruss decomposition problem on bipartite network. So Bitruss model is a well-defined model in existing studies. So in this paper, we mainly focus on solving the efficiency issue on large-scale networks. So we can see the video.
Thank you.
My name is Kai Wang. Welcome to my presentation. Today I will introduce our work, Efficient Bitruss Decomposition for Large-Scale Bipartite Graphs, published in ICD 2020. Here is the outline of my presentation. Firstly, I will introduce what is a bipartite graph or a bipartite network. When modeling two different types of entities, bipartite network naturally arises, such as author paper network, user item network. In this figure, this is an example of author paper network. A bipartite network, butterfly is the smallest non-trivial byte which is an important structure. For example, in this figure, U0, U1, V0, V1 forms a butterfly. Following the definition of butterfly, K-Bitruss is the cohesive subgraph where each edge is contained in at least k number of butterflies. Consequently, we also define the Bitruss number of an edge E, which is the largest k such that a K-Bitruss contains E. So we will study the Bitruss decomposition of a bipartite network G, which is to compute the Bitruss number for each edge E in G. So in this example, the blue edges has a Bitruss number of 2, and the yellow edges has Bitruss number of 1, and the green edges has Bitruss number 0. So Bitruss decomposition can be easily adopted in many applications, including fraud detection on user page networks, and also in identifying nested research groups on author paper networks. And also we can find similar users or items at different levels of similarity on user item networks. Here is the related work. On unipartite networks, there are many well-known cohesive subgraph models, such as Kiko, Bitruss, Clique. On bipartite network, researchers have defined trust-like models, core-like models, and clique-like models. So our model is a trust-like model. And these are two existing solutions on this problem. Here, I will introduce the state-of-the-art algorithm, BITBS, which is published in WSDM 2018. It follows a two-step framework. Step 1 is the counting process. For each edge E, count the number of butterflies containing E, which is the butterfly support of E. In this example, the red edge has butterfly support 3, the blue edge has butterfly support 2, and the yellow edge has butterfly support 1. For example, the edge U3, W2 is contained in only one butterfly, which is followed by what this is U2, U3, W1, W2, which is this one. After finishing the counting process, BITBS will run the peeling process. It iteratively removes the edge E with minimum butterfly support and assigns the buttress number of E as the current butterfly support. When edge E is removed, if E prime shares butterflies with E, and the butterfly support of E prime is larger than the butterfly support of E, we will update the butterfly support of E prime. Taking this figure as an example, firstly, we will remove U3 V4 because it has butterfly support 0. And then it's the V3 U2. And then we will remove U3 V2, which is this edge. And we can see that when we remove U3 V2, the butterfly support of U2 V1 will decrease from 3 to 2 because U2 V1 shares a butterfly with U3 V2, and the butterfly support of U2 V1 is larger than U3 V2. And then we will remove this edge and then this edge, and the remaining are all butterfly support of 2, and then we will remove each edge and assign the buttress number to each edge as 2. Here, we analyze the performance bottleneck of BITBS. We have run the algorithm on 4 datasets. We can see that the majority time cost is the peeling time. And we also analyze time complexity of the counting process and the peeling process. Using the algorithm proposed in VLDB 2019, the time complexity is less than the time complexity of the peeling process. So here arises another problem. Why the peeling process is so slowly? This is because when edge E is removed, the butterfly supports of the edges which share butterflies with E need to be updated correspondingly. And this edge remove operation needs to enumerate all the butterflies containing E to find those affected edges. For example, in this figure, when U1 V1 is removed, BITBS enumerates butterflies containing U1 V1, and it enumerates the combinations of 4 vertices with 3 edges first, and then check whether there exists the 4th edge to form a butterfly. For example, firstly, we will check U1, U2, V1, V2, and the algorithm will check whether U2, V2 has an edge. The answer is no. And then it will check U1, U3, V1, V2. So there are also no edges between U3, V2. And all those check has no butterfly exist. In this graph, there exists only one butterfly. U0, U1, V0, V1. So those checks just return false, which is wasted. Here are the challenges of this problem. Firstly, when performing edge removal operations, it is a challenge to efficiently find these affected edges. And secondly, it is also a challenge to handle these edges with high butterfly support, because when those edges are removed, it will affect so many other edges. So our solutions are as follows. To conquer challenge 1, we propose a novel online index, the Bloom Edge Index, and we propose a bottom-up index space algorithm, BITPU. To conquer challenge 2, we propose the progressive compression approach, BITPC. Firstly, I will introduce the Bloom Edge Index, which is shorted as BE index. A k Bloom is a 2k bicyclic which contains exactly k times k minus 1 divided by 2 butterflies. For example, in this graph, there exists only one Bloom, B0, which is same as the butterfly U0, U1, V0, V1. So we extract this Bloom here and link the Bloom with 4 edges. Here is another example which shows that we can use Bloom structure to compact the butterflies. So the left graph has 2 vertices on the upper layer and 1001 vertices at the lower layer and 2002 edges. So this is a 1001 bicyclic, which is also a 1001 Bloom. So when we construct the Bloom edge index, this graph has only one Bloom, which is B0, a 1001 Bloom. And we will connect this Bloom to these edges in this graph. And this Bloom contains 1001 times 1000 divided by 2 butterflies. We can see that we have compact those butterflies into only one Bloom. Bloom edge index is not only time efficient but also space efficient. The time complexity of constructing Bloom edge index is same as the butterfly counting process, so we can directly run the index construction algorithm after the counting process. And using the BE index, when performing an edge removal operation for an edge E, it needs only pick out the number of butterflies containing E time. And also it is space efficient. The space complexity of BE index is same as the time complexity. And we have tested the index size on WikiIT with 600 billion butterflies. Our index only needs less than 4 GB space. So here we introduce the BITPU algorithm based on the Bloom edge index. So firstly, we will construct the index and compute the butterfly support for each edge E. And then we will intuitively remove each edge with the minimum butterfly support, and we call the remove edge based on the BE index and mark it as assigned. So the time complexity of BITPU is just here is the counting process and here is the pinning process. And this we have significantly reduced the time complexity of the pinning process. So we also enhanced the BITPU with 2 bench-based optimizations, which is the bench edge processing and bench Bloom processing. also propose the BITPC algorithm to handle these edges with high butterfly support. The observation is as follows. Some edges can have very high butterfly supports, though their Bitruss number are comparatively much smaller. For example, the maximum Bitruss number for an edge is only about 6,000 on the delicious datasets, while its butterfly support reaches more than 1 million. BITPC aims to reduce the number of butterfly support updates for those hub edges. And it is based on the following lemma. Given a bipartite graph G, the k-Bitruss of G is contained in a subgraph of G, and the subgraph is constructed by these edges with butterfly support more larger or equal than k. So here is a figure to illustrate our idea. So the k-max Bitruss is contained in the subgraph, which is constructed by these edges with butterfly support more than or equal to k-max. So here we introduce the framework of BITPC. Given a bipartite graph G and the parameter epsilon, BITPC has the following steps. Firstly, we will extract the candidate subgraph, and then we pair the candidate subgraph similarly as BITBU++. This is the BITBU algorithm with these two bench-based optimizations. And in this process, we can obtain the epsilon Bitruss. And then we decrease epsilon, repeat steps 1 to 2 until epsilon equal to 0. Here is our experimental evaluations. We have evaluated 4 algorithms. First is the BITBS, and then is the BITBU, BITBU++, and BITPC. We have evaluated on these datasets. We can see the experimental results. Our Bloom edge index-based algorithms is significantly outperforms the baseline algorithm on all those datasets, and especially on those large datasets, only BITPC can have a result in reasonable time. We also evaluate the total number of butterfly support updates. We can see that BITPC performs the best. Also, the index size is reasonable. In this paper, we propose a novel online index, the BE index, which compares the butterflies into blobs. And we also propose the BITPC to handle hub edges. And we also conduct extensive experiments. That's all. Thank you.
Thank you. Okay, so again, we can entertain one short question.
Out of politeness and fairness, I'll wait for others. If others don't have a question, I'll ask my question.
Okay, let's.
All right, Lux.
Okay, so it's a very simple question. So you mentioned several motivating applications, and by the way, interesting work. Thank you for the talk. And
Thank you.
You mentioned several motivating applications, including fraud detection and possible application and recommender systems. Did you do any case studies, or are you aware of any adoption of this kind of idea in those applications?
Okay, I think I will talk about the fraud detection application. So we not yet verify this model for the fraud detection, but we have verified the cohesive subgraph model on some online platform, shopping platform. Yeah, we have cooperated with Alibaba, so they have a very large bipartite network, the user item network, the shopping relationships. So we have verified the we called a alpha beta core model. It is a core model bipartite network. Mm-hmm. So it has it can be a very effective metric to detect fraud, because those fraud users often forms a connected group. So for the Bitruss model, because this is a recent work, maybe we will adopt on their network soon.
Okay, thank you.
Thank you. Thank you very much. So let's thank the speaker again. Thank you.
Thank you.
All right. Yes. So the next speaker, okay, the first speaker for this section, okay, let me, sorry, wait a minute, I have to go back to my, yes. So the talk will be about Kaleido, an efficient out-of-core graph mining system on a single machine by Zhang Chao, okay, who is a graph system PhD candidate in the Institute of Computing Technology, Chinese Academy of Sciences. So Chang, okay, can you say a few words before we play the video?
Okay. In this work, we are trying to make the graph mining frameworks faster. We proposed a novel view for the intermediate data in exploration subgraphs and design a succinct data structure for the intermediate data. Then we built a lightweight graph isomorphism checking strategy instead of using Bliss like Arabesque and RStream. Okay. Let's watch my video.
Hello everyone, I'm Cheng Zhao. My report is Kaleido, an efficient out-of-core graph mining system on a single machine. Graph data is widely exist in our lives, such as social network, road network, biological network, and so on. Over these graphs, different kinds of tasks are defined to solve specific problems. First, the graph computation apps. For example, the PageRank is trying to find the most important vertex in the graph, and the biggest application is the search engine, like Google. The single source shortest path is well known, and it is widely used in graph database to process queries. These apps calculate values around vertices and all edges. A basic solution is to create a value array for vertices or edges, then iterate and update the value until it gets converged. This kind of problem are also called graph computation problems. The most popular programming model is proposed by Progel, think like a vertex, and many graph computation frameworks followed it, such as PowerGraph, Ligra, and Gemini. The other kind of apps are graph mining apps. For example, the frequent subgraph mining is often used in biological data to discover the highest protein structure. The Clique discovery is usually used in finding abnormal structure in fraud detection. These apps statistic interesting subgraphs. They explore all possible subgraphs, then count which one match the target. So can TLV model still work for these apps? Yes, but it is too complicated. The smart way is treat each subgraph as a basic processing unit. The state-of-art graph mining system Arabesque and RStream follow this programming model. Graph mining is a challenge area. The first one is the exponential increased intermediate data. Arabesque figured out that in FSM over CICEA, the number of subgraphs in each iteration increases exponentially. At the 6th exploration, it produced 1.7 billion subgraphs. Note that CICEA is only a tiny graph. Facing the challenge, Arabesque proposed a prefix tree-like data structure and built a distributed framework. But the data structure brings extra computations, and the distributed framework makes the scalability poor because of the graph's scale. RStream uses a relational algebras model and extreme-based data organization. The relational algebras join operation is the important part in the exploration, but the join operation is too expensive. It produces huge amount of intermediate data. Our approach builds an efficient succinct data structure and uses an adaptive SSD hybrid storage. The other challenge is the isomorphism problem. For example, we try to find a structure like this in the given graph, and we may obtain two subgraphs A and B. A and B are different subgraphs, but they have the same structure, and they are called isomorphism graphs. However, isomorphism problem is a quite difficult problem. It's an NP hard problem. By the way, for convenience, we also call the subgraph an embedding, as following arabesque. Facing the challenge, both arabesque and Artstream use a graph isomorphism library, Bliss. But the problem of Bliss is it is too heavy for checking small graphs. The overhead of it, especially on the memory operations, such as memory allocation, memory copy, and free, cannot be ignored. In Kaleido, we adopt a lightweight isomorphism checking storage. Okay, here comes the overview of Kaleido, a subgraph-centric model graph mining system on a single machine. In the exploration phase, we propose a novel view in handling the intermediate data and manage SSDs as an extension of memory. In the pattern aggregation phase, we use an eigenvalue-based strategy to check the small graph's isomorphism, and specifically produce tree-shaped embedding for large graphs. Let's go with a simple example in Kaleido. Now, we want to find all kinds of 3 vertex patterns and count the frequency of each pattern in the given graph. First, in the exploration phase, we find all kinds of 3 embeddings without repeating. Then transfer each embedding to patterns and count the number at the aggregation phase. In the exploration phase, first get all single vertices, then get all edges. Next, we extend a vertex for each edge, and we get 3 embeddings. The one embeddings can be treated as a one-dimensional vertex set. The 2 embeddings can be treated as a 2-dimensional edge set. So the 3 embeddings can be represented by a 3-dimensional cube. In Kaleido, embeddings can are treated as tensors, so an exploration step can be treated as ascending a dimension on the tensor. For 2 dimensions, store it just like store a sparse graph using CSR or CSC. Inspired by CSR, Kaleido store embedding tensor dimension by dimension. We call it compressed sparse embeddings, CSE. If memory cannot store all embeddings, store the high dimensions CSE on SSDs. At the pattern aggregation phase, transform each embedding to pattern. First, we find the embedding in the given graph, then find the structure of the embedding. Next, erase vertex indices and obtain a pattern. For example, the embedding 1, 2, 3 is transformed as a 3-chain. The 1, 2, 5 is transformed as a triangle. Similarly, we get all the patterns, all the embeddings, and transform it as a pattern. In this example, we're trying to find motifs, so erase the vertex label, because motifs do not need the label info. But for FSM and other mining tasks, the label info should keep and distinguish non-isomorphic patterns. At last, group patterns by the isomorphism. Kaleido designed a lightweight isomorphism checker for small graphs, build a labeled adjacency matrix, and calculate its eigenvalue. Then the isomorphism would be fixed in the combination of the label array, the degree array, and the eigenvalue array. This applies to small graphs. We proved in our paper. What about the larger graphs? We find that the tree-shaped embedding in the exploration hold a majority part, even more than 95% in this dataset. The efficient classic algorithm AHU determines tree isomorphism in time O(n), and then we improve it to support the labeled trees. Okay, let's review the workflow of Kaleido. First, initiate these tasks. Define the exploration depths and the embedding filter pure illegal embeddings. The explore compress embeddings. Then the mapper transfer each embedding to pattern. The pattern filter pures illegal pattern and corresponding embeddings. The reducer statistic patterns. Repeat this procedure till the depth, the application depth is reached. This is our experimental environment. We test FSM, motif counting over, and Clique over the datasets. Compare with Arabesque and ArtStream, Kaleido outperformed them by 13.2 times and 64.8 times. On the other hand, Kaleido is more efficient in memory consumption. This is because the intermediate data is stored by CSE, and the lightweight isomorphism checker contributed as well. Note that in the motif counting, the pattern is no labeled graph, so the memory consumption is nearly equal. As a conclusion, we built Kaleido, a single machine out of core graph mining system. Kaleido offers a subgraph-centric programming API. It's easy to follow. Kaleido uses memory efficiently. We propose a tensor view in handling the intermediate data and manage SSD as an extension of memory. To efficiently check isomorphism, Kaleido uses an eigenvalue-based strategy for small graphs and does a statistic-based optimization for large graphs. Thanks.
Thank you. Thank you very much for the interesting video. So now we have the question time. Any questions from the audience? No question? All right. So my quick question is, so have you demonstrated the use of your API in any application?
Yeah, the applications are used in the FSM motive counting and click discovery, and use especially in the exploration phase and the map reducer, like the pattern aggregation phase.
So what is the benefit, okay, in terms of, for example, usability, to the user friendliness for the programmers?
First, the map reduced, like the API is familiar with most of the parallel programming, and the exploration is easy to follow because you only you need is to define the filter, the true filter in the true phase. For example, the click discovery will only trying to filter the non-click subgraph. It's okay.
Okay. All right. Thank you very much. Let's thanks Chang again for the very interesting talk. Okay.
Thank you.
Thank you. So next, okay, we have the fourth speaker, okay, Mr. Daming Zhu, okay, for talking about finding the best K in core decomposition, the time and space optimal solution. Mr. Zhu is a third-year master student at East China Normal University under the supervision of Professor Shenmin Lin. His research interest is graph data management. Okay, so Mr. Zhu, can you introduce your talk?
Yeah, thank you. A mystery for me is that how can we choose a better K for core decomposition? So we want to find the best K in core decomposition in this work. And we identify several important applications. Hope you enjoy that.
Thank you. Please play the video, yes.
Hello, everyone. In this work, we studied how to find the best K in core decomposition. K-core is a famous cohesive subgraph model, and K-core related algorithms always need a parameter K. It's natural that different K will lead to different output, and the question here is, which K is better, and will better K make a difference? Here, we solve this problem, use the concept of community scoring matrix, which can evaluate subgraph quality. We evaluate K by the quality of the corresponding subgraphs. For the second question, the answer is yes. We have several applications of best K-core. Each of them is very important. For densest subgraph, our algorithm outperforms the fastest approximate solution. For maximum click, our solution is a potential pruning strategy. For size-constrained K-core, our algorithm returns approximate solution in linear time. In this paper, we studied two problems, given graph and community scoring matrix. We want to find the best K-core set. Here, every candidate is not necessarily connected. And we want to find the best K-core. Here, the candidates are connected. Next, I will introduce the problem definition. K-core is the maximal connected subgraph where each node has at least K neighbors, and in the figure, there are 2-3 cores. K-core set is a subgraph containing all K cores, and if in the figure, the circled subgraph is the 3-core set. Coreness is the largest K such that the node is in K-core set, and K-max is the maximum coreness. Coreness can divide the graph into several layers. We define community scoring matrix based on primary values, And primary values here are the number of nodes, edges, boundary edges, triangles, and triplets. Most metrics are based on primary values, and we pick 6 typical ones here. Here, each matrix, if we have higher score, then the subgraph quality is better. Here is the problem definition. Given graph G and community scoring matrix Q, we want to first find the K-code set with the highest score. And second, we want to find the K-code with highest score. And the difference are about the connectivity. Next, I will introduce the baseline solution. In the baseline for best K-code set, we first sort nodes by Coreness to fast retrieve K-code set. Then we compute the score of every K-code set, and we find that 3 code set has the highest score, and we select it as the best. For best K-code set, the algorithm is similar. The candidates are different, but the framework is similar. The baseline runs in O Kmax time n plus Q time, and we found that for a graph whose read time is less than 100 seconds, the baseline spends more than 1 day for some metrics, and it's a huge cost. Next, I will introduce the solution to find the best K-code set. Our intuitions are like follows. Suppose CK is the K-code set, then K plus 1 code set is the subset of K-code set, and we can build K-code set on K plus 1 code set by adding some nodes, and also we can build primary values similarly. Suppose we want to compute average degree and we need the number of nodes and edges. We first add the contribution of those red nodes and get the red delta. Then we can get the primary value of 3 core sets. We then add those green nodes and their contribution grid delta, and we add the delta to the primary value of 3 core set and get the primary value of 2 core set. We do this again, and we compute the primary value of 1 core set based on 2 core set. And then with the primary value of every K-core set ready, we can compute average degree from it. To conclude, in our framework, we compute the primary value of every K-core set with the help of K plus 1 core set, and then we compute the community score from primary value. To handle the delta part, we propose vertex ordering and neighbor query. Vertex rank is to sort nodes by Coreness and break tie by ID. And in vertex ordering, we order all vertices and neighbor set by rank, like what we do in the figure. And we can do this in OM time if we use bin sort. Neighbor query is like this. We ask for this neighbor U with the same Coreness. That means the neighbor constraint is CU equals CV. We can answer neighbor query like this. We first do vertex ordering and build some position tags by scanning the ordered neighbors, and then we can answer neighbor query according to the table and tags. We can return neighbor query in optimal time. Next, it's the score computation for K-core set. We use the framework introduced before. We compute primary value of K-core set based on k+1 core set, then compute the community score. We compute the increment part like this. And for each node V, we compute the contribution of it. And here we use neighbor query to efficiently handle it. And overall, the time complexity is O(n). For triangle and triplets, we use the similar framework. And we count triangles by this. For every VUW in ascending rank, we check if they are triangle. And for triplets, we count the number in two cases and using some particular counting strategy. The time complexity is O(m) to the 1.45, like triangle counting. Next, I will introduce the solution to find the best k-core. A core forest is a forest of k-core tree node, and the k-core tree node stores the vertices with coordinates k in a k-core. And in the figure, we can see a 2-core tree node, and it only contains vertices with coordinates 2. We can construct the forest in O(m) time, use LCPS, and we can store it in O(n) space. We use the structure here because we found that k-core equals to its sons plus k-core tree node. That means if f is a primary value, then we can sum up the primary value of sons and then add a delta, and then we can get the primary value of k-core. In detail, we first build a core tree, and for each tree node, we sum up the primary value of sun and add a delta. Then we get the primary value of every tree node, and then we compute community score from the primary value of tree node. To handle the increment part, we for each V in the tree node, we follow the same logic to k-core set and compute the update. The time complexity is similar to k-core set. Next, I will introduce the experimental result. We use 10 public networks from Snap and Network repository with up to 2 billion edges. We use a quad-core Linux server with 128 gigabytes of memory, and we implement baseline and improved algorithm. We use 6 community scoring metrics. Because there are too many runtime figures, we ignore some in the slide. We turn 6 metrics into 2 categories. And we also turn 2 problems into 1 column. This is to merge similar performance. And in the figure, it's the runtime of score computation. The black bars are our algorithm, and the white bars are the baseline. We find that our algorithm outperforms baseline by 1 to 4 orders of magnitude. And for the orange line, it matches the time complexity of O(n) time. And for the green line, it matches the time complexity of CC. After including the indexing, our algorithm still outperforms 1 to 2 orders of magnitude. And our algorithm can efficiently compute multiple metrics and their combinations because the indexing only needs to be executed once. For densest subgraph, our solution returns the k-core with the highest average degree, and we compare it to k-core APP, the fastest approximate solution. In the figure, the beta value is in bold, and we find that our solution is a half approximate solution, and it outputs denser subgraph on all datasets, and it's faster in 8 out of 10 datasets, and it outperforms the fastest approximate solution. For maximum clique, we still use opd, and we assume S star is the output of opd. We found that for S star, it contains maximum clique in 6 out of 10 datasets, and the size of it is on average 1% of the original graph. And it's a potential pruning strategy for maximum clique. Size-constrained K-core is to find a K-core of size H which contains a given node V. In our solution, we first find a valid K-core with highest average degree, and then we repeatedly peel it and keep it a K-core. In this process, we record the closest size to H. Hit ratio measures how good our algorithms are. And we can see from the right figure that the hit ratio is very high, and our algorithm runs in linear time. Our algorithm will benefit the solution to size-constrained K-core. Next, I will introduce the conclusion. We propose 2 open questions, and we propose a time and space optimal solution for the problem. We can compute score in ON time for matrix other than CC. And we found that our algorithm is very useful in practice. And we identified 3 important applications, and our algorithm outperforms baseline by orders of magnitude. And that's all. Thank you.
Thank you. Thank you for the interesting talk. Questions from the audience? Any questions? All right. Yeah, so I only have a quick question. So can you tell us about the way, or the way you define the best K-core? What do you mean by the best here?
And here, best means it has, for example, the highest average degree, or it has the highest clustering coefficient. And this can be done by you can define what's your best, and you can use definition to find the best K-core. And we just use the K-core structure to identify some like candidates, and then we choose the best K-core with respect to some standards. You can define that standard and then find the best. And we hope that by defining different definition, you can find those subgraphs that meet your needs. Like if you want some property to be better, then you can choose some subgraph with better property, and that's the answer. Yeah.
All right. Okay. So
Randall, is there time for a quick follow-up on your nice question?
okay.
If there isn't, I'll shut up.
Maybe let us make it make the discussion in Slack, right? Okay, because sure. We're running out of time. Sorry.
Thanks.
Okay. All right. So the last speaker. Okay. Please be ready. Okay. We have Gorhausen. Okay, for talking about updates aware graph pattern-based node matching. So Gorhau is a PhD student in the Department of Computing of Macquarie University. His research area includes database and data mining. Okay. Sun, please say a few words about your talk.
Okay, hello everyone. My name is Gorhausen from Department of Computing, Macquarie University. Today I'm very happy to introduce my work, which is called Updates Aware Incremental Graph Pattern-Based Node Matching. Okay, let's begin the video. Hello everyone. My name is Gorhausen from Department of Computing, Macquarie University. Today I'm very happy to introduce our work, which is called update-aware incremental graph pattern-based node matching. So this is the outline of my today's presentation. Firstly, I will introduce the background, and then our target problem, and then our proposed method, which is called UA-GPNM, and then the experiments, finally the conclusion and the future work. So let's begin with the background. Graph pattern matching is originally defined in terms of subgraph isomorphism, in which, given a data graph GD and a pattern graph GP as input, it is to find all subgraphs GN in the data graph that are isomorphic to the pattern graph GP. Here I give a simple example to show what is subgraph isomorphism. So on the left is a pattern graph, and on the right is a data graph. We want to find the matching graph in the data graph. So here in this example, we can find that the subgraph consists of A1, B1, C1 is a matching subgraph of the given pattern graph GP because they have the same kind of load and the same structure. Of course, this is another matching subgraph. Graph pattern matching has many applications. For example, the group finding and the expert recommendation. Suppose that we want to develop a software, and this software needs to be developed together by 4 types of people. There are PM, project manager, SE, software engineer, ACE, a secretary, TE, a test engineer. So, and the project manager needs to be associated with software engineer and secretary. Software engineer needs to be associated with test engineer. So we can model this query as a pattern graph, which is shown here, and we want to find the matching subgraphs in the data graph. So here in this example, this is a matching subgraph, this is another matching subgraph, and this is also a matching subgraph. However, there are some problems of subgraph isomorphism. Firstly, it is an NP component problem, which means it cannot be efficiently applied in big graph. And in emerging applications, it is too restrictive to find matching subgraphs. So to deal with this problem, in 2010, Fan proposed the boundary graph simulation. Boundary graph simulation maps edges in a pattern graph to the passes within bounded lengths in a data graph, instead of edge-to-edge mappings in subgraph isomorphism. So here I give an example to show what is boundary graph simulation. So on the left is a pattern graph. We can see that we have some numbers on the edges in the pattern graph. For example, the number on the edge from B to D is 3, which means the shortest path in the data graph from B to D should be less than or equal to 3. So by the definition of subgraph isomorphism, we cannot find any matching subgraph in the data graph because, for example, the B and the D cannot be connected with D directly. However, by the definition of boundary graph simulation, we can find some matching graphs. So for example, the subgraph consists of A1, B2, C1, D1 is a matching subgraph. And this is another matching subgraph of the given pattern graph GP based on the definition of boundary graph simulation. The subgraph isomorphism and the boundary graph simulation-based GPNM methods aim to find the entire matching subgraphs in that graph. However, in some applications, like the group finding and expert recommendation, people are interested in finding nodes based on a specified structure between these nodes, leading to the GPNM problem. So here I give an example to show what is GPNM. So this is a pattern graph GP, this is a data graph GP. So by the definition of the boundary graph simulation, this is a matching subgraph. And then the PM1, S1, SE2, T1 becomes the matching node of the node in the pattern graph. And this is another matching subgraph. So PM2, SE1 becomes matching node of PM and SE respectively. So as we can see from this example, in GPNM, we aim to find the matching node for each node in the pattern graph instead of the entire matching graphs. Next, I will introduce our target problem. In real life, both edges and nodes in pattern graph and data graph are usually frequently updated over time. For example, when developing another software, the project manager also needs to be associated with test engineer, and secretary also needs to be associated with test engineer within 4 steps. So which needs to be updates of pattern graph. And in data graph, SE1 decides to build a cooperation relationship with TE2, and the DB1 also builds a new cooperation relationship with S1. So this is the updates in the data graph. So when nodes and edges in both pattern graph and data graph are updated, how to efficiently find the GPNM results? This problem is called incremental GPNM. So to deal with this problem, we proposed a new efficient method, which is called UA-GPNM. So next we introduce the UA-GPNM. We realized that there may exist elimination relationships among the multiple updates in both pattern graph and data graph. Here I give a simple example to show what is the elimination relationship. So at first, S1 decides to build a cooperation relationship with T2, but due to some reason, she decides to cancel this cooperation relationship. So although there are 2 updates in the graphs, they won't affect the final GPNM results. So this is a simple example of the elimination relationship. Of course, the elimination relationship is not just limited to this kind of updates. So in our paper, we propose 3 types of elimination relationships. The first type is called single graph elimination relationships in pattern graph. For each update UPI in pattern graph GP, we need to identify the nodes in data graph GD that has the possibility to be added into or removed from the matching results. We call these nodes as candidate nodes and put these candidate nodes into the set of candidate nodes. So given 2 updates UPI and UPJ, if the set of candidate nodes of an update UPI covers that of UPJ, we say UPI eliminates UPJ. So this is the first type of elimination relationship. The second type of elimination relationship is called single graph elimination relationships in data graph. For each update UDI in data graph GD, if the shortest path between 2 nodes has been affected by UDI, we call these nodes as affected nodes, and put this affected nodes into the set of affected nodes. Given 2 updates UDI and UPJ, if the set of affected nodes of an update UDI can cover that of UDJ, we say UDI eliminates UDJ. So this is the second type. The third type is called cross-graph elimination relationships between pattern graph and data graph. For an update UPI from a pattern graph GP and an update UDI from a data graph GD, if these 2 updates keep the GPNM results unchanged, then UPI and the UDI eliminate each other. So this is the third type. Because it is computationally expensive to deliver the GPNM results by investigating each of the elimination relationships among the updates, we build up an index, which is called the elimination hierarchy tree, donated as ES tree, to record the hierarchical structure of the elimination relationships. This index structure can help efficiently detect the elimination relationship between each pair of updates. The detailed steps is that, firstly, for each update, we identify the affected nodes for each update in data graph and identify the candidate nodes for each update in pattern graph. Based on the affected nodes and the candidate nodes of each update, we have the following strategies. The update that has the maximum number of affected nodes or candidate nodes is set as the root of the ES tree. And if the affected nodes of one update UDI can be covered by another update UDJ, then UDI is set as the child tree node of UDJ. As for the update in pattern graph, if the candidate nodes of one update UPI can be covered by another update UPJ, then UPI is set as a child tree node of UPJ. If UDI and UPI can eliminate each other, then we can set the UPI as a chart tree node of UDI, or set the UDI as a chart tree node of UPI. So next, I give an example to show how to build the EH tree. Here we have 4 updates, 2 updates in the pattern graph and 2 updates in the data graph. So for these 4 updates, we first detect the affected nodes and the candidate nodes for the updates in data graph and for the updates in pattern graph. This is the affected nodes, this is the candidate nodes. Because UD1 has the maximum number of affected nodes, it is set as the root of the EH tree. And because it has the affected nodes of UDI can cover the affected nodes of UD2 and the candidate nodes of UP1. So UD2, UP1 is set as the child tree node of UD1. And because the candidate nodes of UP1 can cover that of UP2, UP2 is set as the child tree node of UP1. So this is the final EH tree for these 4 updates. When identifying the affected nodes and the candidate nodes, we need to compute the shortest path length between any 2 nodes, which is very time consuming. Therefore, we propose a graph partition method such that shortest path computation will be processed distributively based on the partitions. For example, here, given this data graph, we divided this data graph into 3 partitions. In each partition, the node that has the same label and the corresponding edges will be put in the same partition. The final process of UA-GPNM is that for each update, we first search the EH tree to detect the elimination relationships. And then we recursively find the elimination relationship for each update. After searching the EH tree, we apply the incremental GPNM procedure for uneliminated updates to deliver the GPNM results. Next, we introduce the experiments. So we compare our methods with the following 3 methods. INC-GPNM. INC-GPNM needs to perform an incremental GPNM procedure for each of the updates in data graph or pattern graph. And the EH-GPNM needs to perform an incremental GPNM procedure for each of the updates in pattern graph. As for the UA-GPNM no partition, it does not have the partition strategy. We use the 5 real-world social graphs, and they are available at this website. The details are shown in the table. This is the experiment results. We compare the average query processing time on different data sets, and this is the comparison. As we can see from this table, UA-GPNM achieves the best efficiency among all the methods. Finally, the conclusion and the future work. In this paper, we have proposed a GPNM method called UA-GPNM, considering multiple updates in both data graphs and the pattern graphs. UA-GPNM can efficiently deliver load matching results and can reduce the query processing time. In our future, we will work on the improvement on space complexity by designing new index structures. And we also want to propose a new approach to selecting the top K matching nodes. That's all. Thank you.
Thank you. So again, we welcome questions from the audience. Any questions? All right, so let me start. Now, in your algorithm, you talk about an incremental algorithm for doing this subgraph isomorphism. I want to ask about in the experimental setting. So how do you get the change of the graph and the change of the pattern? So do you simulate them, or do you get some real data?
Yes, we simulate the queries. We generate like 20 queries for each data set and compare the average query processing time.
Yeah, so if that is the case, then when you have changed from one query pattern to another, so do you add an edge to it, remove one edge, or how many edges are changed every time?
We updated the pattern, or we updated the pattern graphs from deleting one edge to deleting like 10 edges, and based on each query we perform based on each pattern graph we perform the query on each updating data graphs and get the and compare the query processing time.
Yeah. I think this is, I would like to have more information about this, because the performance of the incremental algorithm obviously depends on how many changes you make to the pattern and the graph, right? So
Yes,
there should be a limit, right? If you change many things from the
yes, you are right.
From the graph or pattern, then your algorithm will not work, right? So what is your assumption here?
Your assumption that we for like the developing the for example, for like what I did in the example for like the developing the software, actually the two patterns actually there are some updates in the pattern graphs, but compared with the queries, the updates is not too much. So we have this assumption. And also in data graphs, also we have some updates in the data graph, but compared with the whole data graph, the updates only accounts a small part of the whole graph. Yeah.
Yeah. So I hope that we can find out in the paper how many changes you make, so as to understand how good the incremental, how robust the incremental algorithm is with respect to the changes.
Okay.
All right. So any other questions? Thank you. All right. So if there are no other questions, or if you have more questions afterwards, you can put your questions and discussions in the Slack groups, okay, for our group. Okay. So thank you very much for all your time. Okay, it is quite late now in my zone. Okay, but I hope that you will still enjoy the rest of the talk today. All right. So thank you very much, and hope to see you again. Okay. Thank you, Harsha and Max. Okay, for your help as well. Okay, thank you, everyone. Bye bye.
Thank you.
Thank you.
Thank you.
Thank you. Bye bye. Yeah.
Okay, Harsha, how are you doing?
Good, Professor. We are just moving everyone to the waiting room.
Okay. While you do that, I'm going to make you the host.
Okay.
So I can leave now, right?
Yes,
yes,
thank you.
Professor.
Thank you.
Okay,
thank you very much.
Thank you very much. Thank you.
Okay, Harsha, did you stop the recording?